let's try that again. Now I think everything is good to go. So we are at the end of week 12 here. We've been talking a whole bunch about calculus and the original idea, just kind of core idea of calculus, our sort of definition of what a derivative is and the idea of finding a slope at a point. And then we learned a bunch of derivative rules. So the plan for today, these particular questions here, it might look like a lot, but actually they're not going to take too long to go through, as we'll see. And a little bit about function notation, which isn't a calculus thing at all, but we will be using that a whole lot. So it's good to get some practice on that stuff. Right, so this we'll see, but probably one of the shorter workshops that we've had this semester so far. So some practice with that long version of finding derivatives using the definition of a derivative, then the shortcut fast way using the derivative rules, and then reading a graph and just seeing what the slope would be at any sort of given point of a graph. We've done a whole bunch of talking about that from last week, but let's see if we can do that this week as well. Okay, so we'll start with function notation. And again, this is not really a calculus thing, but if we get something like this, how to just evaluate a function at a particular point. So let's try here. For the one on the left, f of x equals 3x minus 4. And I want to find out what is f of negative 2. How can I find that?
We should put negative 2 instead of x.
Okay, so instead of x. So if we see something like this, f of x equals 3x minus 4. It's just a function like this, y equals 3x minus 4. It's the same thing, but if we write it this way, then we can kind of clearly show if we are substituting in a particular value for our variables. So f of negative 2, I've replaced the x here with negative 2, so we do that in the rest of the function as well. 3 times negative 2 minus 4. And then we just evaluate this. So 3 times negative, I know this is very simple math here, but let's just be thorough. So negative 6 minus 4, negative 10. So just substitute in those values and then see what you get. If you haven't seen this before, we just want to imagine, okay, figure out what the y value would be, so to speak, when x is whatever the thing is in the brackets. So I wrote a bunch here. Maybe we don't need to actually do all of them. Let's try this. When f of 5. So take a moment and calculate that, and then tell me the answer you get. Okay, anyone? We see in the chats. So 11. 3 times 5 minus 4. That's 11. Let's try some more. Let's try the one in the middle here. I'm not going to do all of these. Let's try this one for f of 7. What is f of 7 for this function? Okay, so seeing that in the chat, got that pretty quick, 36. So just 7 squared minus 2 times 7 plus 1. 49 minus 14 plus 1, 36. Okay, let's do this one too. This function for this one, f is equal to f of negative 10, when our x is equal to negative 10. Okay, Nagina got the answer. No one else. Okay, Alisher too. All right. So negative 10 cubed plus 1. So 10 cubed is 1,000. And then we have a negative, but it's an odd exponent. So it's going to stay negative plus 1, 999. Okay. So that's it. Function notation, that's all that's happening. We just say, when we see something like one of these, just evaluate the function when x is equal to whatever the thing is in that function. We did see this a little bit when we talked about interest, and we talked about the simple interest and compound interest. We had AT using the variable t to represent time, and AT is our total value. So we said like a of 3. So this means like, what is a? What is the final value when t is equal to 3? Like this, for example. So that's all this is, not too much to it. Any questions about how we use function notation? Okay, then let's go on with our actual main material for today, which is this to start, the definition of a derivative. So we did this in class, and I am curious if you guys remember. So try to write it out. The definition of a derivative. It's m equals something, kind of a big, long thing here. So we saw that a bunch of times, and we created our sort of shortcut power rule and such from that. But what was the original long thing? So on your paper or whatever right now, just try to write it out. I'll give you maybe 30 seconds or a minute, and then I'll ask you to tell me. Don't look at your notes. Try to do it from memory. Alisher, there's more detail than that. That's just basic slope. We want specifically the derivative version of that. It's longer. Does anyone feel like they remember the whole thing and want to try to tell us?
Yes.
Yeah, okay. And you're not reading from your notes, right? You're doing it from memory?
Okay, it's delta y, delta.
Okay, wait. Answer my question, please. Are you reading from your notes, or are you doing it from memory?
I read only the last part.
Okay, well, tell me the first part that you remembered on your own.
It's limit h equal to 0.
Okay, so as h approaches 0, it's an arrow, not an equal sign, but okay. And?
and then delta y over delta x.
Okay, so that's sort of the easy version of it. What's our long full version of this?
It's if multiplied with a plus h.
Oh, okay, so 1 second. So it's our limit here. So limits h approaches 0. Okay, tell me again the first part.
Okay, it's if multiplied with a plus h.
Okay. Keep going.
Minus if multiply a.
Okay, so are we actually multiplying like f times a?
No, but I don't know how to say it.
Okay, so this is how to write f. So f of a we read in this case. So it's like f at evaluated at a value, but we say it like this. So or this is f
of x.
of x like this.
Yeah, I get it.
Okay. All right.
Okay. Under a plus h or of a or opposite.
We need a little more on the bottom of this fraction.
Minus a.
Minus a. Okay, tell me what is the part that you had to look at your notes for?
It is f of a and the upside.
Just that part.
Yeah.
Okay, that's pretty good. So mostly there. Let's erase this stuff. Okay, so that's the thing. What does that mean? Does anyone feel confident that they can explain what this is?
A, it's equal to x value.
Okay, so let's give ourselves a little graph here, and we'll say, all right. A is an x value. Can we kind of back up a little bit? The x value of what? Let's do a steeper slope. The x value of what?
Of total per no.
No. Does anyone else want to make a guess?
Maybe the turning point. I don't know exactly, but it's my guess.
Turning point is a thing we could find, but this is more general than that.
Can you repeat the question?
So I want you to explain to me what this means. The f of a plus h minus f of a plus h minus a. What do these things mean? Where did we get those from?
From the slope.
Okay, so this is representing slope, that's good. So m, and we kind of can remember here, this is like a y2 minus y1 over x2 minus x1. Okay, so if this is from a slope, then we have a 0.1 and we have a 0.2. Where are those things?
Almost close to 0.
That's the h value. Okay, so we have 2 points. It doesn't matter what they are. So we have a target point on our function. Let's say this point right here is the one that we really care about. What is the slope at this point? Let me just move that a bit so we don't think it's 0. So what is the slope at exactly this point? So we would find that using a tangent line. We just draw this perfectly straight line that touches at that one point. But we need a mathematical way to find out the slope of that line. So this point, we'd say that the coordinates here are A and then f of A. So the x value is, eraser. The x value is A, and the y value here is f of A, which is why we talked about the function notation. It's just the y value at whatever A is. And then we have a second point. So our x2 and our y2 is coming from just another point. Let's say we do it up here.
It is A plus H.
Right, so the x value here is A plus H. And then our y value is f of A plus H. Whatever our function is, evaluated at whatever A plus H is. So H is representing, that's hard to see. Blue. H is representing the horizontal distance between these. So this distance here is H. And it's the distance between the two x values. So H is also delta x. It's the exact same thing. So, and yeah, so H is just representing delta x here. That's the result. It's the difference between the two x values. So that is where our whole idea of a derivative is coming from. We take our slope formula, limit of, or sorry, y2 minus y1 over x2 minus x1. And then we say, let's take the difference between those 2 points, the delta x, and let's just make it really, really small. That's the limit as h approaches 0 part. And then eventually, if we keep doing that, when we finish doing that, once it is incredibly small, the result will be sort of this pink line here. The green line will turn into the pink line, and we will know the exact slope of the tangent at that point. So this is the definition of a derivative here for a particular point A. If we want to rewrite this in a slightly more general way, then we would write it like this. So f prime of x, that's our derivative, is equal to the limit as h approaches 0 of, instead of f of a particular value, let's just say a general x, f of x plus h minus f of x over, and we would have x plus h minus x. So let's just simplify that and write it as h. So on the top, we have y2 minus y1, and on the bottom, again, h is just delta x. So it's still delta y over delta x, and we've added this limit thing in front here. So this form is our general definition of a derivative. There are lots more derivative rules that we will not be getting to in this course, but in a later calculus class, you would do them, and you would keep coming back to this definition in order to see how those other rules can be made. Okay, so that's the idea. That's where the calculus stuff is coming from. I spent all of Monday or Tuesday this week, depending on your section, explaining this in a lot more detail, but this is the short version of it. Does anyone have questions about this concept stuff here? We'll do the actual practice next, but you should try to understand the actual ideas behind this too.
We use this, Professor, we use this grammar only to find the slope.
Only isn't the right word here. This process, it does tell us the slope, but then it turns out there are so many applications of this. Like in a university level math program, you'd spend years just doing calculus and seeing so many applications of this. On your calculator, let's see if I have, do I have a pi button on my calculator? Yes, I do. Okay, this is probably really tiny and impossible for you to see. But right here on my calculator, there's a pi button, or pi. .14159 ... I could press that button here on my calculator, and it's going to tell me what pi is. The calculator cannot perfectly calculate pi. It has to estimate pi. And it turns out the way that calculators do this is with a thing called Taylor series approximations. And that is coming 100% from calculus. That's a big, complex, boring thing I had to study in university. I'm not mean, so I'm not going to make you guys do that. But calculus is very widely used in all kinds of places. It seems really simple, but this idea can be extended to all kinds of things. So I don't like using that word only, because this is only the start of it. There's so much more we can do with this. And we'll get to see some of that stuff in this class, but there's like years and years of calculus study you can do. Okay, any other questions about these concepts?
Yes, Professor, may I ask a question?
Yep.
I don't quite understand where the H comes from. Like, I understand that we have 2 points.
So
But
H,
how do you find?
okay, so your connection kind of broke up a little bit there. You're just asking, where does H come from, if I heard you correctly? Okay, so it's just delta X.
Yes.
That's it. What we need is a way to define the first X value and then the second X value, and we need to connect them somehow. That's kind of the problem. If I said, let's call the first X value A and let's call the next X value B, well, if we put that in our slope formula there, it doesn't do anything to us. We can't kind of combine them. But if we sort of use the same parts, and then also f of a here and f of a plus h, if we sort of have the same parts, if we find a way to connect these two values mathematically, then we can do simplifying and we can do all the stuff that we did before with these. So that's the motivation for it. But the idea is just that h is another way of writing delta x. So if I have 2 points, point 1 and point 2, the x value, the distance, the x distance between them, we're just going to call that h. We could have written all of this as delta x, delta x, delta x. It's just kind of long and it would get kind of confusing. It's easier to think about if we just make up this letter h to represent it. But it really is
just a difference between 2 points.
That's it. It's the delta x value.
Okay, thank you.
That's the only thing. Math people are lazy. They don't want to write limit as delta x approaches 0 and all over delta x every time. They want to find a shorter way, so it's one thing instead of 2 things. That's it. I could have written this a little more simply if I were willing to change some of the variables here, but this is the way that every single textbook and every teacher in the world is going to talk about this stuff. So I'm showing you kind of the standard way of talking about it so you could be familiar with that. Okay, so the definition of a derivative, what we have in the yellow box there, I hope you all have that remembered because we're going to use that a bunch of times here. So let's start. With our shortcut rules, what should the derivative of this thing be, if we remember?
Just 3.
Right, f of x should, f prime of x should be equal to 3. Okay, let's use our definition of a derivative and let's see if we can get that same result, if we can get to that point. So our definition here, so f prime of x is equal to limits as h approaches 0 of, so we need an f of x and we need an f of x plus h, and we also need on the bottom it's just h. That's very easy. So a bunch of stuff over h. What is our f of x equal?
3x minus 4.
Yeah, 3x minus 4. It's just this. Like we don't even have to do anything. It's just given to us there. And probably need some more space. 3x minus 4. That's our f of x. What is f of x plus h?
Depends on h, I think.
But we are keeping h as a variable. So treat both of these things like variables, and then we'll write out what it would be equal to. Okay, so we did the function.
3x,
Go ahead.
like we put x plus h instead of x and then so expand it.
That's exactly what we do. So x plus h minus 4. So that's it. So we're doing exactly what we did for the function notation things. Whatever's inside the brackets for the function f of whatever, you just replace your variable with that thing. So that's 3x plus h minus 4. And then that whole thing minus f of x minus 3x minus 4 and all over h. Okay, so next step, simplifying. Let's open up our brackets on the top here. So let's not eliminate anything yet. Let's just open up all the brackets. What would we have on the top?
Only 3 h.
Sorry, the connection was bad. Could you say that again?
Only 3h, and at the bottom.
Oh, well, okay,
it's h.
no eliminating yet. Let's just open up the brackets. That's all I want to do. We're going to do this in
Okay.
lots of steps.
3x plus 3h minus 4 and
H
minus 3x plus 4.
minus 3x plus 4. So we have a negative and another negative. Those are turning positive. Okay. And this one is pretty easy here. So now we can see lots of things are going to eliminate. We have 3x minus 3x. Those are both gone. We have a negative 4, a positive 4. Those are both gone. And we're left with just 3h over h. Okay, what's our next step for eliminating?
H will go with the H.
Okay, so h divided by h, those just cancel each other out. So limit as h approaches 0 of 3. And now what?
Like h cannot be 0 because it's in the like bottom, right?
Is there an h on the bottom of the fraction here?
No, no, no. Like before elimination, we have h.
Okay, but at this point, what are we left with at this point?
If the H, if the X equal to 3, then the slope will be equal to.
It doesn't matter what the x value is. The slope will always be 3. So at this point, what we want is to get rid of the limit. In this case, it's very easy because we don't have h. So the limit as h approaches 0 of 3, there's no h anymore. It's just 3. That's the only thing it can be. There's no h influencing anything. So at this point, the thing the limit is connected to, h is gone. So the limit has no meaning. So it's gone. We don't have to evaluate it evenly or even. It's just erase it. It doesn't mean anything anymore. So the answer is just 3. So we do our simplifying, and then the goal when we get to a step like this is always get rid of the limit. There are a few different things that could happen, but this is the easiest case. We just don't have h anymore. Just don't write the limit. Just erase it. It's gone. Okay, so we got our shortcut method results. We said that the slope should be 3. And again, look at our original function here. This is mx plus b. So y-intercept is -4. Slope is 3. It's a straight line. This is the m value. So we know that the slope is 3. And again, the first derivative tells us the slope. So of course, the slope should be 3. And that's exactly what we got. So lots of ways that we can confirm that we've got the correct answer here. But good to kind of go through the process and sort of convince ourselves that, yes, this does actually work. Okay. Let's do the second one here. We can do this a lot faster since we just did one like this on the left, and then we'll go to a more complex version here. So f prime of x is equal to limits as h approaches 0. Sorry, before I write this, what should our answer be?
-2.
-2. Slope should be -2. Okay. So on the top here, I'm not going to write out the thing on the side to help you. You tell me, what is f of x plus h?
-2x minus like
Let's
negative
before
2x
the expand,
minus.
let's not expand. Let's just keep the brackets in there.
Okay, brackets, and inside the brackets x plus h and minus the given function. Negative
You're
2x
missing
plus
something. You forgot something.
no. Like there is minus, and
You're still missing something that needs to come before that.
because of minus, it will.
What's going to come here?
I omit 1
Plus
plus
one.
1.
Yes, the +1. Can't forget about that part. Or well, it will cancel out, but we need to show mathematically that it cancels out. We can't just forget to write it. So +1 there. Okay, and that whole thing over h. limit h approaches 0. And if we expand all this, negative 2x minus 2h minus 2 plus 2x. Sorry, not 2. Plus 1 minus 1. And that whole thing over h. And we can see what's happening here. The negative 2x, positive 2x, positive 1, negative 1. And we are left with limits h approaches 0 of negative 2h over h, and limits h approaches 0 of negative 2. No more h, so just negative 2. So this thing is telling us for this function, the slope is always negative 2. And again, mx plus b form here. So y equals mx plus b form. So negative 2 is the slope. This is exactly the answer that we should expect. Okay. So once we've done kind of one of them, doing another one of them gets a lot faster. Okay, I'm going to give you a moment in case anyone's writing, and then we'll go to the next ones. Okay, next pair of questions. Let's do this one on the left here first. So again, using our shortcut power rule, if we remember it, what should this be equal to? Or what should our derivative be equal to?
2x minus 2.
2x minus 2. All right. So let's write this whole thing out again. F prime of x is equal to limit h approaches 0. And the bottom's going to be h. And on the top, what are we going to get?
X minus 1.
Where is x minus 1 coming from?
I think it's x plus h squared.
Okay, so x plus h squared.
Minus 2 multiplied by x plus h plus 1.
Finished?
No, and then minus.
All right, so I'm going to write larger brackets here, minus.
X squared minus 2x plus 1.
Plus 1. Okay, so we didn't actually do an example like this in class where we had multiple separate terms. So this is kind of showing that our power rule thing is going to work here. But we can still do that here, and it's not going to be, sorry, not our power rule, it's sum rule. So not going to be too hard here. Okay. So limit as h approaches 0, and we need to, let's just expand all of our brackets here, and then in the next step, we'll do the simplifying. So let's expand our brackets one by one. What's first?
X squared plus 2xh
Plus 2xh
plus h squared
plus h squared. So that's our x plus h squared expanded. Good. What's next?
Minus 2x
Mhm,
minus 2h
mhm.
and plus 1.
Plus 1. Okay, that's the first part. That was the f of x plus h. And then the rest of this, just a negative sign in front. So we just switch the signs on everything. So minus x squared plus 2x minus 1. Okay, so very long.
Professor, isn't it minus 2, negative 2 instead of plus 1?
Where are we looking? Which you're talking about this part here?
Yeah.
So look at what the function was. I made that mistake when I was writing this out in the previous one. So it's negative 2 times x of x plus h, and then afterward plus 1. The plus 1 is not inside those brackets, is afterward.
Okay. Thank you.
Okay, so all of that's over h. All right, so we need to simplify. Tell me some things that you notice that are going to cancel out.
It's x squared
All right, so
and
x
negative 2x
squared, negative x squared. What else?
and negative 2x
And the positive 2x,
plus
the plus 1, and minus
1 and minus 1.
Okay. All right, so let's rewrite with that stuff just canceled out. 2xh plus h squared minus 2h and all of sorry, let's gather our terms and clean that up a little bit. H squared, and I want that at the end. Let's do it this way. 2xh plus minus 2h plus h squared. Okay, so that will work out nicely with our next step. What is our next step at this point?
We substitute like separated common factor of h and cancel out.
Good. So we have a common factor of h on each term on the top now, which will happen every time for these polynomials. And I'm just going to combine those two steps. We have an h on the bottom, so those will just cancel each other out. So we are going to lose this h and this h and this h, and then one of these h's. So this, it won't be h squared, it'll just be h there. So 2x minus 2 plus h. Now what?
We put 0 in the place of h.
Okay, so this is the stage. In the previous examples, we said we could just kind of erase the limit because it didn't apply anymore to our function. But at this stage, for these kinds of functions, it still does. It's still there. We still have an h in our function here. So we need to evaluate the limit. Up to this point, we just kind of ignored the limit, but now we have to evaluate it. We do that by just doing what the limit tells us to do. Set h equal to 0. So that's 2x plus 2 minus 2 plus h is now equal to 0. So just plus 0. And we can see that's just going to disappear. So 2x minus 2. So the result here is that f prime of x, our derivative function for the original, is 2x minus 2. And that's what we got with our shortcut rule there. So same result. Okay. Right, let's do, or let's give you a moment if you need to write. Okay, let's do the next one too. I think this is, yeah, this is the last long one, and then we'll use the shortcut rules, so it'll get a lot faster after this point. So try to write out this step, the equivalent of this step for this other function here. So before any of the expanding, just kind of put in all the parts, and then if you have time, you can try to start the expansion as well. So I'll give you 1 minute, and then I'm going to ask you to tell me what that first line will be. So go ahead. Okay, who can tell me what this first line will be? And Mirabos has been answering very well so far. I would like to hear some other people give an answer. I want to make sure everyone's understanding this. What's our first? Go ahead.
Should we tell an answer or a formula?
I want the whole thing, like this,
Uh,
for this actual function here. No, I don't mean whole thing is like the final version, but just this next line, or this first line here.
limit h approaches 0 to x plus h squared plus x plus h minus 3.
Plus h squared plus x plus h minus 3.
And minus 2x squared plus x minus 3.
Squared plus x minus 3. Okay.
Over h.
Over h, good. And then if we expand all of those parts, can you tell me what?
Yes, 2x squared
Mm-hmm.
plus 4xh
Mm-hmm.
plus 2h squared plus 8 plus x plus h minus 3 minus 2x squared minus x plus 3 over h.
All over h. And what parts of this are going to cancel out?
2x squared.
Okay.
X.
X and x.
3.
And the 3's. Okay, so basically anything without an h term is going to get canceled out. And that makes sense because it was f of x plus h minus f of x. So kind of the f of x part of the x plus h, and then with this minus f of x, that makes sense. So those two should eliminate. It's really just the plus h part that's going to stick around. So the rest of it should cancel out, but don't just skip it. Make sure you write it and you do confirm that that happens. but in these cases, all that should eliminate. So just kind of from our intuition and kind of logic, thinking about this, all the parts without h being eliminated makes sense. All right, so limits as h approaches 0 and for x h plus 2h squared plus h. Do I have that right? Yeah.
No, it's not plus h. There is no h. And yeah, sorry.
We have it here, this little plus h right here. Okay, so like with the previous examples, common factor of h on the top and the bottom. At this stage, it's all just kind of the exact same thing. So take out the common factor of h and we will be left with 4x plus 2h. And what's going to be here?
+1.
Plus 1. So h over h, most of the time they're just kind of disappearing, but here that's 1. That's not 0, so it's not gone there. Okay, so plus 1, can't forget that's on the end. And then we will set our limits. All right, not write the limit. We will we'll evaluate our limit. So we set h equal to 0 for x plus 2 times, excuse me, 0 plus 1 for x plus 1. And that is exactly what we should be expecting from our shortcut rules here. F prime of x, product rule, 2 times 2 for x minus 1 for the exponent, so 1, and then derivative of just x is 1. There we go. Okay, so that's some more long versions of this. You can do the long version for all kinds of these things. I don't have like a x cubed or a larger function as an example because they take forever to do. Still possible, should still get the same results from our power rule, but just want to kind of save us some time. We have those shortcut rules for a reason, because they're much faster. We're just doing this definition with these sort of easier, more simple examples to get the practice of using this, to again, just see the logic behind this and why this works. All right, I am going to take a quick check what else I have here. 1, 2, 3, 4, 5, 6. Okay, we're doing pretty well for time. Does anyone have questions up to this point that they would like to ask? No. Okay. So let's take our first break here. It is 8:28, almost 8:29. So we'll come back at 8:39 and we'll continue and start using the actual derivative rules and those faster versions of it. So come back at 8:39, everyone. Mirabos, I saw your question about extra explanations about polynomials. Can you tell me what exactly you're thinking of? Which things about polynomials are you confused about?
I'm thinking of properties like local minimum, local maximums. I know others, but
okay, with the derivative side of that stuff, or just visually recognizing it?
Just visually recognize.
Okay, so we did talk about that last week a little bit. I don't have slides ready with new ones of those, but I can re-show you the ones that we looked at before. And we can talk about those. Where are those? Week 11, day 2. I think. Yeah. Okay, so this kind of thing, and just where, sorry, where the minimums and maximums are, or like classifying them, or everything. Is there a particular part?
Like, I know where is maximum or minimum, but I'm going to ask about what is local minimum and the local maximum or global minimum.
Just look, okay, sure. All right, so in this case, for this example here, how many turning points do you see?
Sorry, can you repeat your question?
How many turning points do you see for this graph?
4.
4. Okay, so 1, 2, 3, 4. Let's number them here. 1 and 2, 3, 4. So number 1, is that a maximum or a minimum?
It's maximum.
Okay, so maximum. Number 2, what type is that?
It's minimum.
Minimum, okay. 3 is a maximum, 4 is a minimum. Let's start with number 3. So global versus local. Can you tell me what your guess is about that?
I think it's local because it's less than 1.
Less than 1? Which
or like no, it's the more bottom, right? Like first one is in the 3.5.
I see. Lower than the number 1 turning point. Okay, so good. If we just draw a horizontal line across, is there any point on the function that is above this line? Well, yes, all of this. All of this stuff is above, so it's clearly not the highest of the minimum, clearly the highest of the maximum points. Okay, so good, that's local. And let's look at turning point number 1 here, the other maximum point. What do you think about that one?
About 4.
Number 1, this one here.
It's global because it's the highest. Am I right?
Okay, so you could be, like, the way we've defined global is a little bit unclear, admittedly, or the word global in this case. It is the highest of the turning points. It is the highest maximum turning point, but we don't really care about that. The important thing is it the highest overall point of the function? So global maximum would mean if I draw this horizontal line across, that there is no other point on the function anywhere, not just maximum points, but any point on the function that is higher than this line. Is there a point higher than this line?
No, I think.
What's happening on the far right side of the graph?
It's like going to infinity.
Okay. And what's the y value of this turning point number 1 here, approximately?
1. Y intercept?
Yeah, or the y value. It's not an intercept, but
for first turning point?
Yeah, so like 3 points, I don't know, 3.6,
7,
3.7.
3.7.
Yeah, around there. Okay, so which number is bigger, 3.6 or infinity?
Infinity, of course.
Okay, so same question again. Is there a point on this graph that is higher than turning point number 1?
So that means it's not global, right?
Right, it's not global. It's because on the right side, there, if you see any point anywhere on the function that is higher, like this point right here, up here in the top right, that's higher. That point is higher than this maximum point. It is not the overall highest point of the function. Therefore, it's a local maximum. That's the only thing we care about. Is it the overall highest point or global minimum, the overall lowest point? We're not only comparing it to the other turning points or to the other maximums or minimums. It's just the overall pattern of the graph. So the two minimum points that we have, what types are those?
And-
Local or global?
Are they same, like the same rule for them as like maximums?
Yeah,
And
same
if the
concept,
rule is
just
same,
flipped
it's the
upside
same.
down.
And they are like locals too. They are local minimums.
Right, these are both local minimums because way here on the left, far left side of the graph, it goes down to negative infinity. That's lower than these other 2 points. Okay, so these are all local. These ones. So looking at these 3 graphs, tell me if, okay, so we see lots of local minimums or maximums. Tell me if you see any global minimums or maximums.
Exercise 30, global minimum point, turning point.
Sorry, which number? Which exercise?
36.
36. You see a global minimum, you said?
Yes.
Tell me the approximate x value of it.
More than 2.
One more time.
Just more than positive 2.
Okay, a little more than positive 2. Good. So this point here, it's a minimum. It's also the overall lowest point of the function. So this one here is a global minimum. Do we have any other global minimums or global maximums?
I think we have not global minimum or maximum.
Okay, good.
That's
The
all.
rest, yeah, so the rest are all local because the rest here are going to infinity and every other direction. This is the only point that, this is the only function that could have a global minimum or a maximum, or only a global minimum. So that's it. Just the local idea is quite simple. Global means not just turning points, but overall for the entire function, anywhere on the function, including the ends that go off to infinity. Including those, is it the overall highest or lowest point? Yes or no, that's it.
Okay, thank you, Professor. Like, may I ask about homework? Like, you wrote derivatives,
Yep.
and should we use the way that we have used in this workshop, or just we can write the answer?
You can use the shortcut methods. That's the next thing. The exponent rules. Oh man, some of those, those would take a very long time to do if you did them with the original. Where's my? If you did them with the definition of a derivative, that's way too long. So these derivative rules we're going to practice right now. You can do these for the homework.
So we shouldn't give the definition like be long equations, right?
if you really want to, sure, but it's not necessary. Okay, so you'll see exactly how we solve the questions here. That way is perfectly acceptable for the homework. Okay, it's
Okay, I don't.
okay, so just as soon as you see these examples, it'll make sense. 8:40, so I'm going to resume. So power rule, sum rule, constant rule. I have a set of a number of sets of examples using these, and we'll get some practice. First, let's actually write them out. So for I just had them written there. Can you tell me what the rules are, or the names of them?
Constant rules, sum rules, and power rules.
Okay, constants, sum, and power. All right, let's start with the constant rule. That one's pretty easy. Can you give me the definition, the whole rule?
The constant is always equals to 0.
You got the ideas. I want you to be a bit more careful about your terminology.
Sorry. Y equals to C.
Okay, so if y equals c, then
Y derivative.
Y prime, we read that as
Prime. Yeah.
Yep.
Prime equals to 0.
equals 0. Okay, so that's the formal statement of it. If y is equal to c, if y is a constant, then the derivative of that constant will be just 0. Okay, sum rule. Can someone tell me what that one is?
F of x plus.
I want the full statement of it again.
Y equals to if y equals to f of x plus. Can I use another letters or?
If you want, yeah, doesn't matter.
Plus, let's say h of b.
Let's not use h because that has sort of special meaning for our derivative stuff.
Okay. B of a. Okay.
Okay.
B of g. No.
I like what you're doing here, and choosing a different letter for the name of the function is totally fine, but the variable that we take our derivative with respect to, that has to be the same. This kind of question where we actually have two different variables happening turns out to be a much harder kind of question. So if it's x in the first one, it should be x in the second one.
Then b of x.
Okay, so some other function which we call b of x or z of x or m of x or whatever. Okay, so if y is equal to function 1 plus function 2, f of x plus b of x, then
Y prime equals to f prime of x plus b prime of x.
b prime of x. Good. So if the function is has inside of it two different parts added together, then just find the derivative of the two parts separately, then add them together. That's sum rule. And the kind of most complicated one that we have, power rule. Can we get a definition of this?
If y equals, can we use f of x squared? Or do we have
you want to be more general than that?
maybe just x squared.
More general, not just, it's not
X
just squared.
of the power of n.
Okay, so x to
N power
any exponent, we'll call it n.
then y prime equals to n multiplied by x to the exponent n minus 1.
N x exponent n minus 1. Okay, this is true. I want to add one more thing to this that would still make everything stay true. Just a bit more detail.
Constant, we can say a.
Okay, so we can have some coefficient in front, like a x to the exponent n, then y prime would be equal to a times n for our coefficient, x to the exponent n minus 1. So often we do have a coefficient, but it's very easy to deal with. So it's nice to just put that in as well as part of our definition of this rule. Okay, those are the three rules. Or there are so many derivative rules. If you look at like a big formal calculus textbook, there are tons of them for all the like cosines and the trig stuff. And it's like bringing back nightmares, all the ones I had to remember. There are lots, but we can do quite a bit with just these three. So these are the ones we're going to focus on in our class. Okay, so these three, gonna erase them. Hope you have them written down or remembered. And let's put them to use. So at this point, these don't take too long. You guys should be able to try to do these on your own. So I'll give you a few moments and try them, and then we'll talk about them. So both of these two, find the first derivatives of each. Okay, let's try these out. So our first one, if our function is f of x, then our derivative is what? Let's practice saying the left side of this as well. So tell me the whole
f prime of x equals 3x, right?
3x squared. So we have a constant there. Constant rule says that thing's going to turn into 0. So it's just 0. It's gone. We don't need to write it. Power rule, 3 comes down, becomes our coefficient. Subtract 1 from our exponents. It's 2. That's it. Let's do our next one. And I showed you some different notation stuff in either yesterday or today's class, depending on your section. So let's get used to some of that as well. We saw this dy, or this is f of x, so I guess we write it this way. d over dx of f of x. What does this thing mean? What does this represent?
This is also derivative.
Just the
These two things are the exact same. Okay, exact same thing, just a different way of writing it. Okay, so d over dx of f of x is equal to
negative 6x.
Negative 6.
negative 6x
Minus 7.
minus 7. Okay, again, constant is disappearing. We have an x here. We have a coefficient of 1 on that. Subtract 1, then x to the exponent 0. That's just 1. So 7 times 1, that's just 7. So if you have a coefficient of 1, then that variable is just going to disappear and you're just left with whatever the coefficient was in front. Okay, pretty easy here. But again, let's get used to kind of writing the left side on here so we don't get confused about what these things are actually representing. Next two. There we go. So a little more here. I want you to find the first derivative and the second derivative for both of these. Go ahead. Don't forget the one on the right. Okay, that was 2 minutes. Let's try these out. So the one on the left, what is our first derivative?
14x.
Okay, so let's again practice reading out the left side as well. So f prime of x is equal to 14x. And our second derivative?
F double prime of f of x equal 14.
14. There. That's it. That one's pretty easy. And our one on the right, a little bit longer. what is our first derivative?
F prime of x
F prime of x
equals 9x squared plus 4x plus 1.
or x plus 1. Good. And our second derivative.
F double prime of x
Mhm.
equal 18x plus 4.
18x plus 4. So second derivatives, third derivatives, fourth derivatives, you just keep repeating the derivative process here. We don't really go too deep. Usually just do a second derivative. I'm going to talk more about that in class next week, so I won't say too much about that here. But this thing, as I just said, and as we heard, if there are two here, second derivative, we'd read this as f double prime. Double prime. F double prime of x for a second derivative. And y double prime and all the other things. The dy over dx notation gets a little more complicated for second derivatives. That's also a thing I'm going to talk about next week. Okay. Question?
Yes, I have.
Yeah.
Like with first derivative, like we found the slope of a quadratic function, right? And for second derivative, what can we find?
That is an excellent question. That's exactly what the preview question is about. I think I posted it already on our classroom page, and that's exactly what we're going to talk about next week. So that's exactly the right question to have. I don't want to tell you the answer yet. I want you to start thinking about it and give me your answer for the preview question.
Okay, Professor.
Sorry to keep you in suspense, but I don't want to spoil the fun early. All right, two more of these questions. I want you to find the slope of this function here. So f of x equals 2x squared minus 3x. Give me the slope of that function at this point, at x equals 3. And then same thing here. So we just kind of had these examples earlier. I want the slopes at these 2 points. So go ahead. what is our process here? How can we find the slopes of these functions?
We substitute.
We're gonna do substitution, but tell me a bit more precisely. Substitute what into what?
Substitute x to this function.
This into here?
Yeah.
Okay, so f at 3 is equal to 2 times 3 squared minus 3. What do we have? 9, 18. So 18 minus 3, 15. So the slope is 15.
No, we should use derivative rule firstly, I think.
Okay, so remember that a function like this, f of x equals 2x squared minus 3, that's the same thing. It's maybe easier to think about as y equals 2x squared minus 3x. So if we substitute x in here, or 3 into these values of x, we are getting y. We are getting the y coordinate. So we're just getting the height of the function. We are not getting the slope. If we want slope, we need to use the derivatives. So if you substitute your x value into the original, you get the y value, the height. If you substitute it into the derivative, you get slope. So our first, what is our first derivative of this function?
F prime x
Mm-hmm.
equal 4x minus 3.
4x minus 3. Okay. There's our derivative. That's the function that is telling us the slopes of this original function for anywhere on the function. Now we're going to solve this when x is equal to 3. So f prime of 3, so just substitute x into this function, is 4 times 3 minus 3, 12 minus 3, 9. So this is the slope here of the original function, our 2x squared minus 3x. When x is equal to 3, slope is equal to 9. Okay, so when we do the second derivative stuff next week in class, then this whole thing's going to get more confusing. We're going to have x values, and we have to be very careful. Do we substitute our x values into the original, into the first derivative, into the second derivative? And like, we could do all of those things. Which one gives us which information? So if we want slopes, we put our x values into the first derivative. We got to remember that part. All right, next one over here on the left. So we already found the derivative of this first derivative. F prime of x is equal to 3x squared. And what is our slope when x is equal to 2?
It's 12.
12.
12, we say. Okay, so f prime of 2 is equal to 3 times 2 squared, which is 3 times 4, which is 12. Okay, so for this function, x cubed plus 1, when x is equal to 2, then our slope is exactly 12. Okay, so that's our process here. We take our original x value, put it into the first derivative. So the original function is only going to tell us the height. And then we'll see another thing that we can do like this with the second derivative in next week's classes. That's these examples. Does anyone have more questions about these examples? Okay, so the other parts that I have prepared here, there are more of these practice questions in our textbook. What's it? So these are most of the exercises that we're working on. There are more in those pages, and I have kind of a more detailed recommended list on our classroom page. Let's get back to where we were here. So last bit, I want to do a bit more practice about just reading a graph and kind of seeing what slopes are or are not at various points. Okay, so also a practice of function notation here. Let's try these. So let's try this one here. This looks like a nice easy one. So for this function we have over on the left, can you tell me what is f of 2? Just give me an estimate by looking at the graph.
-6.
-6. Okay, so to be very clear how we're getting that. So f of 2, that means that x value is 2. So x value at 2 here. And we're just looking down. And okay, here is the point where x is equal to 2. And just look over. What's the y value? Looks like it's right about -6. Okay, what about when f of 1? What does that equal?
-3.
-3.
Looks like -3. How about f of 3?
-2.
-3.
-3.
Yeah, it looks like I'm not sure how good the resolution is when you guys are looking at this through Zoom. It looks like this would be 3 here. It looks like it's kind of slightly below that. I don't know, maybe like a -3.5 or something. A little bit lower than that. Okay, what about f of 0?
-2.
Looks like it's right about -2. I think maybe the maximum point is happening like slightly to the right of that. So maybe a tiny bit less. Let's just say -2. Or just estimating approximate values here. What about f at -1?
-5.
-5 would be here. I think it goes a little further
6
down.
maybe.
6. Again, okay, it's a little easier for me because I have a nice high resolution version of this. I still see a few dots, maybe like -7. But again, we're estimating. Okay, so those are just the y values. That's the easy part here. Let's try these other ones. F prime of 2. What would this value be?
0.
Okay, why are you saying 0? How do you know that?
Because the slope is flat at that point.
Okay, so it looks like the slope is flat. So that point is, again, here. So we're still looking at the same point of the function, but now we're not asking about the y value. We're asking about the slope. So we imagine ourselves drawing a straight line that touches the graph at only that point. And I know it does touch way over here as well, but we don't consider that. So it touches only there in a local sense. Let's just move this line over in case that's confusing anyone. So like that touches at only that point. And then what is the slope of that line? Approximately, that looks like a flat. I know I drew it flat, but it does look like we have a flat slope or pretty close to a flat slope at that point. Let's try f prime of 1. F prime of 1. A little harder to estimate, but just give me a general number.
I think it's 1 because it looks like 45 degrees, maybe.
Here?
Maybe 3.
Okay, so again, I'm going to draw a line. If I draw a tangent line, I guess it would look like about that. So drag that over. So that looks like, to me, again, not perfect, but that looks like it's touching at exactly the points where at x equals 1. So right there. What does the slope of that line look like?
4.
Is this a positive slope or a negative slope?
No. Negative.
Negative. Okay, so give me your answer again.
-4.
Okay, so this looks like a slope of -4 approximately. Again, we're just estimating. But if I were to put it down on the grid like this, it looks like it lines up about like that. Roughly -4. Okay, so at the very least, we should be able to see it's a negative slope. Definitely, that should be right away. And also, -1 would be a slope of like exactly kind of a 45-degree line like this. It's steeper than that. So it's more negative than -1. So it's going to be a kind of a bigger negative number. The 4, again, that's a little harder to estimate, but at the very least, negative and more negative than -1. Okay, how about when f prime of 0? What do we think that looks like?
It is 0 also, I think, because it's flat.
0.
Yeah, it looks like we have a maximum point there or very close to there. So it would be the slope of 0, or maybe the maximum point is over a tiny bit. So probably 0, or maybe like a -0.1, sorry, positive 0.1. So it might be slightly positive. We might be a tiny bit before that maximum point, but very, very close to 0, whatever it is. Okay, so some more harder ones here. F prime of -1. That's probably the hardest one. If we're making our estimate of f of 1, if we say it's right about here, so our y value is 7, and we try to draw a tangent line there, what do you think that slope would be?
Is it undefined or?
Infinity or 0 or undefined.
Okay, can it be undefined? Can it be a perfectly vertical line?
No, it's just a little bit.
A little bit less. It cannot be a perfectly vertical line. That would not be a function. Like with however this function is defined, it's f of x is like an x cubed something with some sort of large coefficient in front. I don't know, 10x cubed or something. So if we look at the function mathematically, it's impossible to have a situation where the same x value gives 2 different y values. They'll always be unique. So it can't be undefined. An actual function with curves like this that we have, it will never have a perfectly vertical undefined slope. It can be a giant number. It can be a slope of like 1,000,000 or so big that we just call it infinity because we can't even measure it. It can be that, but it can't be undefined. Okay, so let's just draw a super vertical line like this. And it's going to look like that. This slope is actually not that big. If we kind of look at the line that I've drawn here and just kind of estimate this based on our grid, 12, I don't know, 30 maybe. Even a smaller number like this, 30, the slope ends up looking like really, really steep, and it's hard to tell the difference between them. We don't need to be able to guess 30, but we should know big positive number. Positive, way more than 1, some big positive number. Okay, last one here, f prime of 3. What does that look like roughly? This is our point here. What's your guess for the slope?
Maybe.
20. Okay, so big positive number. So positive something, he's saying positive 20. That approximately looks like a tangent line, I think. About there. And what's the slope of that thing? That's from there to therefore. That looks like a 6 or a 7 maybe. Doesn't really matter. 6. Big positive number. That's enough for us to be able to recognize. If we want to know the exact slope, use the first derivative. We have that tool now. It's actually not that hard to use. We have our power rule and just substitute in the number, pretty easy. So if we want to know the exact slope, that's what we're going to do. But visually, we want to be able to see these sorts of patterns here. Okay. So I'll just kind of ask these sort of same questions in a slightly different way. For what region of the graph is the slope negative? From where to where on this graph is the slope negative?
From -2 to -6.
And tell me in terms of the x values.
From 0 to 2.
Okay, so about there to about there. So where x is 0 to where x is equal to 2. These are all negative slopes. Some very negative, some just like a very, very close to 0, but those are all negative. Okay, and then for the other intervals here and over here on the two sides, all positive on the other sides there. That should be a thing that we just immediately recognize. Where are they positive? Where are they negative? And then where are they 0 at those two turning points? Okay. That's as accurate as we need to be for estimating the values of the slopes. That will be enough to let us see what's going to happen with our second derivatives and stuff. Okay. Anyone have additional questions about this example? All right. So That's it. That's what I had. There are more of these questions again in our textbook. There are more listed right here than what we actually did today. And there are more as well described on our classroom page that you can go through. But just the definition of a derivative thing is useful to know, and that will definitely come up later. But for now, if it's confusing for you, then just focus on those derivative rules, the power rule, sum rule, constant rule. We are going to be using those in every class. So you need to be familiar with finding those, finding derivatives using those tools. And you are going to get lots of practice with that with the homework question. Questions 3, 4, 5 on the homework are all about finding derivatives. And the preview assignments, which I mentioned. For this image, we have 3 different graphs, blue, green, and red. And then, so when the red function is doing certain things, tell me what is true about the green one and the blue one. So where the red's positive, where the red's negative, and where the red is 0. So that's exactly what the whole second derivative thing is about. Okay. Does anyone have remaining questions they would like to ask? Yeah.
Professor, may I ask the question about the debate, because I couldn't ask it yesterday. My internet was not really good.
Sure. Let's just wrap up this and then we can talk. Does anyone have questions about this workshop and what we talked about?
Excuse me, Professor, I have a question about homework.
Okay.
Could you, thank you. In the part 2, question 4b, I'm a little bit confused about the question.
Okay. Yep. 4b.
Yeah, it is y in exponent 4 minus 1 divided into y. And is it like only in the second part, is it only y in exponent of 4 or 1 over y overall in the exponent of 4?
You should be able to answer that. Order of operations. Order of operations. Which thing comes first, dividing or exponents?
Exponents.
Okay, so answer your own question. Is it 1 over y to the exponent 4, or is it 1 over y all to the exponent 4?
I think the first one.
It's the first one. 1 over y to the exponent 4. So order of operations, that comes first. But the other thing that you said would actually be the same because it's a 1 on top. So if it were 1 over y to the exponent 4, that would be 1 to the exponent 4 over y to the exponent 4, which would be 1 over y to the exponent 4. So in this particular case, your question doesn't actually matter. It's the same result either way, but order of operations, formally, it's this thing.
Thank you, Professor.
Welcome. Any other questions? Okay, I'm going to wrap up. If you do have more questions, just hang around and ask, and we'll talk. Thank you for coming, everyone. I will see you in class on Monday or Tuesday, or maybe in the debate tournament if you're joining tomorrow night. Goodbye.